I'm here in New York City, and my goal for this weekend is to try and build my own RFID tag. If you saw the video I made about finding the cashierless store in Yiwu, China, you'll know that I took apart an RFID tag to see how it worked. And one thing led to another, and my friend Stuart challenged me to make my own RFID antenna.
I mean, you said before, it's going to be easy, right?
Well, that wasn't quite what I said. I don't think it'll be that hard. And as far as all good dares go, this one is about to go way, way too far. I'm here in New York for the HOPE conference, which stands for Hackers on Planet Earth. It's one of my favorite conferences, and I thought this RFID project would be the perfect thing to bring with me to see if I can, well, nerd snipe some other really smart hackers into helping me. It's really 2 parts scavenger hunt and 1 part hacking and debugging. And well, I've been cheating a little bit. Okay, I've been cheating a lot. First, we need to go back to the scavenger hunt part. This all started about 2 weeks ago when I was still back in Shenzhen, China. One of the problems I didn't yet know how to solve was how I was gonna get these little tiny chips that power the tag. And well, serendipity struck, because I got an email from Gail, the director of marketing at Impinj, which is the company that makes the RFID tags. Let me read you that email. Hello, Scotty. It was fun to see my inbox and text messages light up with so many people from different parts of my life who saw your video on the cashierless store in China, starting with my 16-year-old son, who is a huge fan of yours. John, the guy who designed the antenna you looked at, is eager to tell you just how complicated that job really is. Our indie product manager, Max, wants to send you a developer's kit. And Mark, our Monza product manager, offered to show you how to build an antenna out of a paperclip. You made a bunch of nerdy Seattleites happy yesterday. But we started exchanging emails, and I started to worry that maybe they didn't really understand the lengths that I was willing to go to make something like this work. So I had some work to do. I found some packaged Impinj RFID chips on Taobao. I also learned from Impinj that they use what's called ACP, anisotropic conductive paste, to attach the chips to the aluminum antennas. And so they said, you know, you're gonna need a fairly big, industrial, expensive machine to do this, probably not something you can bring to a conference. After a little bit of online research, I found that it's actually used also in repairing LCD screens. And so I did what I always do when I have a weird, unspecified question about cell phone repair supplies. And I went to Schwan of the Tool Brothers. It turns out they use ACF instead of ACP. Film instead of paste. We are headed to try and go find ACF, but it has to be in the refrigerator. It has to be cold.
Yes, yes.
So it's not here in the markets because there are no refrigerators in the markets. So he took me up to their office up in one of the office towers, and they had some ACF that I could buy, as well as gave me a demonstration of how their machines work. Okay.
That's it.
Oh, there we go.
Yeah, okay.
I'm out. Now, the boss that designs these machines said the same thing that the Impinj guys said, which was that I needed a lot of heat and a lot of pressure to make this work properly. But the question is, if I wanted to do this improperly, could I still make it work? So I described all this to Stuart over dinner, and well, one thing led to another, and we ended up back at my apartment at like midnight.
So I've collected a whole bunch of crazy things. I've got a crazy soldering iron contraption, chips, aluminum foil in various very thin thicknesses, and we're gonna give this a shot.
So what's the goal? Are you kind of trying to make the same outline?
Yeah,
As that?
I figured I'd just trace it, cut it out, stick a chip on it. Boom, done.
Done.
Here's the chips that I got, which are in like the plastic package for soldering them to circuit boards. Just totally not what we're gonna do. Because we have aluminum, and you can't solder to aluminum. It just doesn't stick. We're gonna put down ACF. It's like super fancy. So this is a Tool Brothers special. This is a regular soldering iron with the big tip taken out, and this crazy T-bar contraption with a silicone pad in the end of it supposedly we can use this to tack down the ACF. Should we stick to the foil first?
I'd be tempted to just put 2 pieces of foil and make it like a foil adhesive sandwich. But
Unit. That is my silicone pad here. Oh, that's so good. I did not. That was not in the realm of possibility of the things that I thought might happen.
There we go.
It looks pretty toasted, doesn't it?
Yes.
That's just a sliver of foil we cut.
Yeah, that's a thing. I declare victory and think we should. How will we test it with a? Is there a way to test it to the IC?
Have we got any other things that we could try to bond to it, like some SMT components?
Sure, I have a bunch of passives.
Yeah. So
All right.
something like that.
Yeah.
Okay, so right now we have a soldering iron with a modified tip that's too hot.
I mean, I probably could
Because
just
right
use
now
a solder
you-
gun,
yeah,
just
right, yeah.
use the Heiko
Yeah.
even. Actually, let's do that. We'll put this right there on the Heiko.
That's just.
Yeah,
Okay, so that's pretty
on
good.
there. All right. So let's do a test.
Oh man.
Dude! The most important thing that I wanted to figure out is this ACF approach at all viable?
Yeah.
And I think definitively I can say yes, ACF with a soldering iron is not a completely crazy idea.
Foil. Right.
I think what the thing to do now is to send an email to Impinj being like, I have figured out how to bond the chips to aluminum. Can I have some, please?
Wait, how about bonding an IC to
That aluminum?
aluminium antenna? Because that is an
That's
antenna.
not a crazy idea.
I think we should give that a go, man.
I did not expect that to work. So, I mean, I guess I don't really need bare die chips to make this work.
No.
What's the first one?
Actually, I don't really need anything other than to sit down with an X-Acto knife at this point. Thank you
That
for
was-
a crazy adventure.
That was great. I was
Um,
consider me impressed thus far.
So at this point, I'm pretty confident that this is definitely possible. I sent some pictures of the Frankentag that Stuart and I put together to our friends at Impinj, and they got super excited. And they said, okay, not only are we gonna send you a dev kit and a reader and some sample tags, but we're also gonna send you like a bunch of bare dies and some stuff we scraped off a wafer and everything I really needed to go to the lengths that I really wanted to go. So right now, I'm on my way to the Hotel Pennsylvania to set up the microscope for the conference and see if I can convince some hackers that are smarter than I am to help me build working RFID tags. We're here at the Hope Conference in New York. I'm here with Simon, who says he doesn't want to be on camera. And so Simon has hijacked this. He said, well, why don't I just use a loop of copper as an antenna?
Yeah, so I managed to tin the pads of that small encapsulated chip, and I've attached a strand of a copper wire on one pad. Right now I'm trying to bend it to a line so that I can attach the other side. And then it would have a loop, and maybe that's enough to power the chip. So I think it solders on properly. It just chips off super easily.
So Simon, you have said that you're ready to test. You finally got it soldered. Do you want to bring it over here? So I've got the reader running. Okay, that one can read. Oh wait, no, wait. Oh yeah, that's reading.
That is the sketchiest tag ever.
That is amazing. I would not have guessed that that would work. Simon, who does not want to be on camera, has successfully soldered a working antenna out of just like a copper coil. That is super cool.
So proof of concept is really sketchy antenna still works.
Yeah.
It's really sketchy antenna.
Yeah, so that gives me hope that like, as far as it comes to antenna design, like the two ends need to connect.
Yeah.
And that's
Anything
about
goes.
it. Now I'm feeling kind of silly for spending all of this time like sourcing ACF and aluminum and like all of this stuff, yeah. Could have just hooked up a wire. So just so I understand here, you're going to take one of the iPhone 7 headphone adapter boards that I made for the iPhone headphone adapter video, and you're going to try and turn this into an RFID tag.
Why not?
By soldering an RFID chip to it. That is super awesome. And you're also the guy who, as a teenager, bought a mainframe and dug out your basement to fit it into your basement?
In my parents' basement.
Parents' basement?
My father helped with that. They weren't on board originally, but when it showed up at the house on a trailer, they pretty much had no choice but to go along with it. So this is the little loop we had to make to get a loop in the circuit for the antenna. But otherwise, the chip's just soldered to the back there, and this should be a functioning RFID tag. It's reading. I can get it off.
That is incredible!
Tell us what's going on here.
So, we just were curious as to what was going on with these RFID tags. In the development software, you can see that the tags are responding on different frequencies, and it's seemingly random. So we wanted to see what the transmitter was doing, what kind of frequency hopping it was doing. So we busted out a software-defined radio, and we're looking at about 30 megahertz of bandwidth. The colors indicate signal strength, and these really strong signals here are the transmitter. If we stop the transmitter, you notice that the spectrum clears up.
I am finally, after all this experimentation and good hacking fun, gonna sit down on the last day here and try and make a working tag that more or less looks like this. Gonna cut it out of aluminum foil, try and bond it with the ACF, see if we can get it to read. I'm just gonna use one of these tags as a template to get the shape of the antenna correct. Pretty close, not bad. Now I need to cut a little slit here and bond in my chip. Now I need my ACF. So that should be enough just to tack it down, and then it'll lift off. So now I think what worked before when I was playing around with it with Stuart was put the chip down first, upside down, and then put the aluminum foil over the top, and you can sort of get the pads aligned better. So what is this ACF stuff anyway, and what makes it so interesting? Why not just use solder? So 2 reasons. The first is that we're making the antenna out of aluminum, and solder just doesn't stick to aluminum, so we have to use something else. The other reason, and this is what makes ACF really special, is that it only conducts electricity in one direction. It only conducts electricity vertically and not horizontally, which is pretty darn magical. And I want to explain more about how that works, because I didn't understand when I first got this stuff how that could possibly be. But I'm gonna need some props, so hang on. Okay, so here's the deal. Anisotropic conductive paste has these teeny tiny conductive particles in it. We're gonna use cheese balls as an example. Now, the conductive particles get sandwiched between 2 conductors like this, and they get squished just a little bit so that they're in compression and they're pushing on the 2 outside surfaces. Now, a cheese ball is conducting from the lower surface to the upper surface, but there are a bunch of cheese balls. So if we put too many cheese balls in, then they all touch each other and they conduct horizontally, like that. But if we spread them out, like this, then none of them touch each other, but they all touch the upper and the bottom surface, like this. Now, why is this important? And the reason it's important is that it's used when you have a bunch of different conductors, say my fingers like this, that you don't want to touch each other, right? So you want this, let's say this is a pad for like a ribbon cable on an LCD, right? You want all of these to be electrically separated, but you have another set that you want to stick to them, and they're all right next to each other. So how do you put paste or film down without conducting from one to the other? And that's where ACP or ACF comes in. So you end up with balls on each of the fingers, and maybe some in between, but because none of them are touching, like this, you don't end up with any continuity between the fingers. Isn't that cool? Now they use it for attaching flex cables to the backs of LCD screen glass. They also use it for RFID antennas when the chips are tiny, tiny, and they're bonding bare die chips onto an antenna. Oh man, I'm covered in cheese powder now. I should have also bought napkins. Let's try it. No. Oh, it works.
Holy shit.
There it goes. You should totally make one.
Yeah, I mean, if you can teach me, then anybody can do this.
Yeah, that's good.
All right.
And then just hit it with the soldering iron.
Yep.
So the challenge is you don't have much of a gap there. You'll see when you get the chip in there, it's going to be too narrow.
Yeah, that should be good.
Oh, that is,
Nicely done.
that is a good feeling. It doesn't look like much, but there's been like 3 days of people here at this table trying to make this happen. It's a good mixture of like electronics and arts and crafts.
Okay, so I think we can totally declare success on this. We have a whole bunch of other tags we made this weekend, but there's one thing left to do, which is to properly test this. Well, it's been fun, New York City. I am on my way to Seattle to go see Impinj to put these RFID tags in their anechoic chamber and see how well we did, as well as talk to the guy who actually designed these antennas. Impinj is nice enough to fly me to their offices to test out the antennas and tags we made in their anechoic chamber to see how they perform. I wanted to be extra clear on this. I'm not being paid to make this video, but Sume did give me a free microscope, and Impinj sent me a whole bunch of chips and a reader and a dev kit, and they're paying for the flight out to Seattle. So I just wanted to be careful to disclose that and make sure that it didn't seem like I was trying to sneak an advertisement by you guys here.
100% full.
I'm really excited to test these tags out, but I'm also really excited to learn more about people who actually know what they're doing and do this for a living, design these antennas, and learn more about the chips that power them.
Hi.
How are you? Nice to meet you.
Welcome.
Likewise, thanks.
Mark.
Mark, good to meet you.
Nice to meet you.
Mark.
You must be John. Nice to meet you. I'm Scotty. So, I brought you guys the tags that we made in New York. I don't think it's quite what you guys are expecting. And so that was modeled off the one that I found on the beer can, right?
Yep.
So off this one.
Yes.
That's really cool. Did you trace it or?
Yeah, I just used this as a stencil on top of the aluminum, and then used ACF for the attachment. So
ACF.
like ACP,
Oh,
but film instead of paste. And so I thought the first thing that would be really cool to do is to just test these out in your test environment.
Yes.
And you can tell us how good or how bad each of these antennas
Sure.
are.
Right.
Wow.
So we're in the chamber. This is what you call an anechoic chamber. There's acoustic version, there's a radio frequency version. This is our small chamber. So it's just good for RFID tag testing, really. This is designed to just pretty much emulate an infinite space. So anechoic, just by definition, means no echo. So if you have anything in the space, then it's going to bounce back. So you're eliminating that, meaning you got an infinite open space that's clean. And it also shields everything that's coming in from outside.
Should we start by testing one of the tags that you
Yes,
guys
let's
made,
do it.
and then we can test the ones that I brought
Yes.
with me and see how they compare?
So yeah.
Okay.
All right.
So what this is doing is at every frequency, it's modifying the transmit power and looking at the minimum power for the tag to turn on.
Yeah.
So it's shifting, and we've got certain resonance frequencies So this is called power on tag forward, or that minimum power for the tag to turn on. So the lower the level here, the lower this number, the less power that's needed for the tag.
So the better the tag's performing.
Right. Yeah.
I want to talk more about that, but first, I want to try the
Yes.
things that we designed and then we made to see how they compare to what you do.
Let's do it.
Well, let's start with my copy of your antenna.
Okay.
When you were testing, were you pretty close range?
Yeah.
So if you have this loop, if you have the chip connected, when you're in close range, it's pretty much the magnetic fields that are working together. This long portion, it gets you that long range portion of it. So you can have something that works close range and then doesn't work long range.
Yeah, okay.
So
so it's not reading at all.
No, it's not responding.
All right. In the meantime, let's try Patrick's. Oh man, nothing. Let's try one of the circuit boards because this is actually soldered. Oh man. So nothing there. Okay, this is the one that doesn't have a loop at all.
So the other one, let's see if it does any better.
This is definitely humbling though.
Don't worry. Like I did antenna work in grad school, but it took me 2 to 3 years before I was proficient.
Really?
Yeah. So,
After grad school.
Yeah.
Yeah. So this is the loop that you guys built with a paperclip radiator that Joey made. Really? Nothing. So you're gonna sanity check these for us, Mark? Here?
Yeah.
See, because we didn't get them to read on the other.
We didn't.
In the anechoic chamber.
But
Okay.
this one's reading,
Okay, good.
and this one's also reading. So that tells me that they're working close range near field.
So they weren't damaged in shipping.
Not to the point where they don't work at all.
I mean, to be clear, like I don't think we did a particularly good job at this. so I'm not convinced they're any different than they were last weekend.
Okay.
But I think what I'm hearing from you guys is that I shouldn't quit my day job as a YouTuber and go into business making RFID tags, that maybe I should leave that to you guys. So honestly, one of the things that's still fuzzy to me is like just the basics of like how a passive RFID tag works, because these tags don't have batteries in them, right? But they have chips that are powered by electricity.
Yes. Yeah.
And that honestly still seems like magic. And I was wondering if you guys could give me like the expert's explanation.
Sure. Okay, so this tag is a transponder.
Okay.
It takes the signal that comes from the air and it responds back to a reader.
Okay.
So you'll have a reader, which I'll represent with this box. So let's say we've got this tag here.
Yep.
This antenna will receive the signal. It's going to backscatter a response back.
And as part of that signal, it's generating electricity that's turning the chip on, right? Because normally the chip is just off, like there's no electricity.
Yeah.
One way I've been trying to mentally picture this is, okay, so the tag is turning RF energy into electrical energy that's powering the chip. Seems like one way you could do this is like charge up a capacitor. So store up some energy, and then the transmitter stops transmitting, and then you transmit back out on the antenna.
Sure.
I get the sense that maybe that's wrong.
So what's actually happening here is it's modifying if the energy is going into the chip or not.
Okay.
So it's doing open, close, open, close.
Yeah, so it's pretty much reflecting high or reflecting low. So it's like a mirror, no mirror to a light. It's the exact same idea.
Okay.
Yeah.
Okay. Well, should we go learn more about how you guys design tags? We've learned a lot about how I am bad at designing tags.
There's a few steps to it. There's one is a primitive prototyping process where I use actual copper tape. So it's not that different from what you did. I'll probably cut out that H61 design. So that's actually the copper
This looks
tape.
like a craft vinyl cutter.
It really is. It's
that what it
exactly
is?
what that is. So right now I'm just aligning the blade so it'll actually start at the same point.
Okay.
And then we just tell it to cut.
That's awesome. That's fast too.
Yep. So we just peel away what's unnecessary, and then we actually take one of the inlays and then actually solder on like a little strap. All right. So now get the soldering iron heated up.
So you're just peeling up the extra copper.
Right. Exactly.
That's not part of the tag.
Yep. So this is same as primitive etching, if you want to call it.
Yep.
So there you go. Oops.
Wow.
And then I just pull out the center, and there you go.
That's great.
Yep. So I just take this length out from here.
That's already got the chip?
Yep.
Oh.
So that's why I recycle the unused, chips that I've already.
Precision with this.
And then I just solder across.
That is super simple.
Then, you got a working prototype. So actually, probably one of the interesting machine that we have here is actually this machine. Again, it doesn't look that different from your station, right?
Yeah, except that it's got a needle.
Yep, so the needle is actually a vacuum tip.
Okay.
So it actually helps us pick up these tiny chips that you've seen already.
Right,
So
yes.
this actually here is actually ACP in a liquid form right now. It's uncured.
So this ACP is the paste version of the film that I use.
Right, precisely.
But same deal, just different.
Same exactly. It's
different
heat
form
activated.
factor.
It's just fluid. You pick up a chip. You have to do all the flipping and positioning.
Yep.
And when you come down to a chip, like there's usually pads. There's actually 2 gap, and you have to place the chip in the middle. Yeah. So right now there's actually a resistor with this power source that actually if you see this plate of light come up, it's actually heating it. So we're actually put the inlay on top of it while we press down with it. That's actually a pressure sensor.
Yep.
So we put it down, put the chip, glue, chip, and then hold it, and while we heat it, and then it actually cures it. Takes about 30 seconds.
Okay.
So I just took some ACP onto just dental pick, and then just kind of put a just little bit of drop, and then onto where the chip is going to land. And then now I'm actually heading over to where the chips are, picking up using a vacuum tip. So now I just picked up a chip with the active side down. I'm navigating over to where the inlay gap is. Push down, press the foot pedal, and then it actually starts curing it. Takes about 30 seconds. So, all right, there you go. There you go.
There we go.
It's alive.
It works. So
Okay.
this rig is you're taking these bare die chips off the wafer. They've been sliced.
Yep.
The wafer's been sliced up, and you're attaching them to what?
2 inlays. So these, let me show you some of the prototype inlays.
Yep.
So these are actually etched copper.
Okay.
It's a typical PCB etching process. We actually asked them to etch it on a 2 mil substrate, and they come like this.
Yep.
And we can replace it with aluminum, work exactly the same way.
Okay, so copper versus aluminum doesn't matter.
Nope.
So thank you guys so much. This is super cool to see how you do it and realize that actually it's not all that different than what we tried at Hope.
Really.
But one thing that occurred to me as we were doing all of this is that it seems like as much of the wisdom that you're putting into the antenna design, a lot of the magic that's happening here is actually happening inside the chip.
Yes.
And so I guess I was wondering, can we learn more about how that works?
Yeah. Let me toss you over to Varsha, who's actually overseeing a lot of the manufacturing process that we actually do.
On the chip side?
Yep.
Okay, awesome.
All right.
Yeah, let's go talk with her.
Yep.
So I'm Varsha, and I'm responsible for all the silicon manufacturing. We are a fabless company, as you can see. Fabless means, it's just an industry term. It refers to no fabrication. We are just a design and test house. So that's what we have here in Seattle. We have the design team for the chip, and then we have some testing, some final inspection. But we rely on our suppliers overseas primarily to do all of the manufacturing. So that's starting right from the foundry that builds up the design that you've given them on the silicon wafer, and then taking it through the entire back-end step where you go through testing, then you put down your connection layers in the back end. You know, you could grow bumps or you could grow large copper pads like the ones you saw, and then it keeps going into singulation. So this is what the wafer is coming out of the foundry. The wafer basically starts with just silicon. The raw material is sand. On the beach, basically, and it goes through a lot of sophisticated processing, and you build what you call a silicon ingot, which is basically these long cylinders of silicon, which then get chopped up into like some industry standard thickness. Yeah, so basically you start with the raw material as this, and then the design, which is the IP, just gets printed onto it, and the technology behind it is actually very, very sophisticated. Just to give you an idea, just to build this RFID chip, which is relatively simpler compared to like a microcontroller or something, there's easily over 100 operation steps that it goes through in the foundry.
And they're building up different layers and then etching them away, is that the right
Exactly, yeah. And we get this wafer back for testing.
Got it.
And
so is that what's come into sitting here in this room?
Yes, so the wafers out here, these
Yep.
have come in for testing. Well, if you had to guess, how many die do you think are on this wafer?
Yeah,
Yeah.
like thousands? Maybe more?
Thousands is conservative, sure.
Okay.
So yeah, that's one tag.
That's teeny tiny. This
So-
looks like maybe a quarter of a piece of normal glitter.
Yeah, so basically to give you an idea, the thickness of this wafer is basically equivalent to a strand of human hair.
Okay. Yep.
So there's about 100,000 die, over 100,000 die on this
Over
wafer.
100,000 dies. And so do you guys test every single die on the
Yes.
wafer?
We test every single die on the
Wow.
wafer. So we have the EG probers back there, and so we have these test sites that we land on. So in each of these, each of the shots, you see these couple of die that look a little different.
Yeah.
And so basically, those are our test locations. So the probe cards, they're actually, the tips are like cantilevers on there. And so basically, you basically land on the ATIs, and it enables you to test multiple die at the same time. And then from there, it moves on to what we call the back-end process.
Okay. Yeah.
The back-end process is what enables you to get the wafers to the end product that goes out to a customer.
Okay.
So you need to, what comes out of the foundry
Yeah.
is not enough. You actually have to build on it. So repassivation is our first step in the back-end process. And basically what that's doing is it's putting down a thick layer of like a polymer. And the purpose of this layer is as the tags get picked and placed, there's different bonding forces that get applied on the inlay manufacturing machines. The repassivation basically acts like a buffer. And then the second piece is the metal, the large copper pads that you saw. So basically when the chip is coming out of the foundry, you have a couple of regions, what you call the bond pad, where the top metal, where the passivation, the passivation layer is opened up, because that's how you make metallic connection to your tag. But that usually tends to be very small coming out of the foundry, hence the back end kind of takes that and enhances it. So usually people grow tall copper pillars or gold pillars if you're in the automotive industry. In order to singulate, this is a really thick wafer. If you have to start dicing through this, it's going to take forever to get through it. So you need to thin it. The reason the foundry wafers come out at this thickness is it's just, it's sort of an industry standard for handling with all the robotics that are out there. I'd say like 200 microns or so, silicon starts getting floppy. So, and that's when it starts needing extra help. Like this is definitely under 200, which is why it's on a carrier.
And this is like a flexible tape, right?
It's like a polyolefin, Everything that gets thinned and diced will invariably go on a carrier of some form. And then at that point, it goes on for singulation. And the
singulation is literally just cutting it apart.
Chopping it up. Do you want to guess how long that takes?
So, well, let me get clear on the process first, so I have an informed guess.
So there's multiple technologies out there. The mechanical saw is, the mechanical diamond saw blade is the most popular. And then through
but the saw blade is like a essentially thin piece of wire, right?
Actually, no, it's like a little, it's like a disc.
So it's sort of like a pizza wheel.
It's like a pizza wheel, exactly. It's a pizza cutter. Yeah, exactly.
So I'll guess like a couple hours per wafer.
Yeah, that's pretty close. I'm in about there. Yeah, about like an hour-ish a wafer.
Can you give us a sense of sort of what at the like design end of the process? What are you guys doing that makes these chips so tolerant to a wide variety of antenna designs? Is this more of a Mark question?
Do you want to take that, Mark?
Well, yeah. I'm not in the design space for it.
Okay.
A lot of the complexity in the design is in the impedance value in the chip, how well it's able to respond, automatic tuning capability, we call it auto tune, where the chip can tune its front end impedance automatically as it's powering up. There's a lot that's going on behind the scenes there for designing the NVM, designing the RF front end, and then there's the controller piece that is translating the signal coming in to writing and reading information from the tag.
Okay. Is that sort of the main three sort of logical parts of one of these chips? Okay.
Yeah.
So RF, controller, and then memory.
Yep.
Okay.
Yeah, and it's effectively, you could think of it like a piece of memory that you can access from 10 meters away.
Which is a totally crazy thing.
Yeah. Completely passively.
Like, this is super cool, and thank you so much for sharing with me a whole new world of electronics.
It is. Been around for decades, and it still amazes me.
I bet. Thank you.
Yeah, absolutely.
So, this whole journey for me has started with like buying a can of beer and taking apart the sticker on the label in this cashierless store in China. And that's really the only use case I've thought of. Can you just give us some idea of like what else do people do with this stuff?
Sure. So within our technology, there's some industries that have adopted it more heavily. Retail is one of the biggest ones.
Okay.
There's challenges in knowing where their products are currently. If you were just using the barcode, you need line of sight. You need to match up. But with RAIN RFID, you no longer need line of sight. You can get in the order of meters of read range. So if you're using a handheld scanner, you can sweep a wall and get it. Another example would be for luggage tracking.
Okay, yeah, it looks like you've got like, I know what this looks like.
The airline wants to make sure that they know when your luggage came in, that it went to the right location.
Awesome, so I guess you guys have some other demos as well.
All right, well, we've got a product demonstration here that Gary will happily run you through.
This
what do we
is
got here?
Shipment verification is the use case. So what I'm gonna do is I'm gonna wield this box, right?
Okay.
So when we talk about shipment verification, imagine this is a pallet, right? And we've got a shipment going onto a truck.
Okay.
And so I have a little line there on the floor.
So I'm standing on.
Right, and so you're the inside of the facility, let's say.
Okay.
So I'm coming off the truck here, so this is the out. And the idea is that I want to know two things. I want to know what has crossed the line, and I want to know when it's crossed the line. Right now I'm reading the box here, nothing's happening on the screen, and I only want something to happen once we cross the line. So as we move across here, we should see the screen update to tell me that these items have moved across. And that's kind of the challenge, is that it seems really simple, but again, I think you've seen, we can read around 1,000 square feet, so you get a lot of coverage. We're probably reading everything in here.
Cool, and then you got one more demo for us?
Yes.
Right? Max, you've got the last demo for us here.
That's
and
right.
I hear you're doing something cool with Raspberry Pis.
That's right. Yeah, so this demo is built around one of our embedded reader modules.
Okay.
So it's basically a RAIN RFID reader built into a little package.
Okay.
And you can add it to a device to add RAIN RFID functionality to that device.
Okay.
So we've got one of those RS1000 reader modules on a circuit board that's in a Raspberry Pi hat form factor. And what that means is I can just plug it into a Raspberry Pi, and then I've got a reader, right? I put that on the network, I plug in power, and I can read the tags nearby and send the tag reads wherever I want.
Okay.
So in this case, we've got two of these things in different locations, and they're sending tag reads up to the cloud. I've got a bunch of household items that are individually tagged, and then I can ask my smart speaker, which has a skill that goes to the cloud, you know, where's my stuff?
Okay.
Alexa, ask Impinj, where's my wallet?
Wallet is located near the table.
Oh, okay. So it's over here in the second location. I can take it over to the first.
Okay.
This is the quote-unquote island. Alexa, ask Impinj, where's my wallet?
Wallet is located near the island.
All right, nice. So now I just need like a ton of Raspberry Pis to put through my apartment.
That's right, and Raspberry Pis are cheap.
Yeah, okay. Yeah, this is pretty awesome. Thank you. Well, cheers, guys.
Cheers.
Thank you so much for having me and for the day and sharing all of your wisdom and sending me parts and code and knowledge. And thank you for helping me prove to Stuart that it is actually possible to build your own RFID tag. I thought I would come down here to beautiful Lake Union as the sun's going down, just to sort of wrap things up. I guess the first thing I want to say is, Stuart, I don't quite understand why you thought this would be so hard to make your own RFID tag. I mean, it's particularly easy if you don't really care how well it reads. It really was more of a scavenger hunt than it was like a debugging and engineering process like some of my other projects have been. I want to thank everybody that's come along with me on this adventure and helped me along the way. Thanks to Impinj for flying me out here to Seattle and putting me up, and for sending me all sorts of gear and chips and advice and giving me access to their labs and engineers. Everyone that I talked to who worked at Impinj was just super awesome. Thank you guys so much. There's a link to their website in the description below if you'd like to learn more. Thank you to Sume for donating the microscope. If you guys would like to learn more about that microscope with the built-in screen, there's a link to her AliExpress page in the description. Also, thanks to Stuart and Laurie and everyone at Hope, Mitch and Patrick and Jeremy and Joey and who else am I forgetting? Robin and Simon and Connor and Glitch and Mitch and Lady Red
and everyone else who came by and hacked RFID tags with me and played with the microscope and provided me advice and helped filming. It was probably some of the most fun I've had at a conference. You all are amazing. And lastly, thanks to all of you for coming down this weird rabbit hole with me on this crazy adventure that started with taking apart a sticker on the side of a beer can at a weird cashierless store in Yiwu, China, that's led me literally halfway around the world. If you've enjoyed this video and you want to come along with me on other weird technology adventures all over the world, hit that subscribe button down below. I'm Scotty from Strange Parts, and until next time, stay tuned for more adventures. I'll see you again soon. I forgot one more quick thing, which is I wanted to say thank you to Evan, who is a Strange Parts fan, who helped me out yesterday filming in the Impinj offices. Thank you, Evan. You're awesome. And thanks for hooking me up with your mom, who works at Impinj, which is a big part of the reason that I got to come out here. So thanks. So I wanted to thank Sumei, my microscope seller lady in Shenzhen. She was nice enough to donate this microscope for me to bring to Hope to do all this awesome hacking that we've done all weekend. I had 2 promises that I made to her. One was that I would tell all you guys about it, and if you would like a microscope from her, she's super cool. She sells cool microscopes for reasonable prices. There's a link in the description below. But also the second promise was that the microscope would go to a place where it would be well loved. And Jeremy and Joey are part of a hackerspace in Texas?
San Antonio,
right?
Texas.
Yeah, San Antonio, Texas.
10-bit works.
10-bit works.
It works.
And you guys are open to the public?
Yeah.
Anybody wants to come?
Anybody that wants to come, it's we work on a sliding scale, and we've had a lot of success bringing in people that would not normally go into a hackerspace, and do all kinds of cool stuff.
That's awesome. So I'm really happy for this to go to a good cause where a lot of people are going to love it.
Thank you very much.
You're welcome.
We really appreciate it.
Yeah, and thanks to Sumei for
thank you, Sumei.
Thank you.
She's awesome.